Okay, and welcome to part 2 of the Fundamental Theorem of Calculus. And in part 1, that'll be explored in another video. And this is going to give us the opportunity to see how we can evaluate definite integrals, and we don't have to mess with those RAM methods, which are not only, what's the words I'm looking for, not only are they, well, shall we say, estimations at best, but also difficult to navigate around sometimes with the different methods and which one's best. So in order to get the fundamental theorem of calculus under our belt, we have to start with a function that is continuous at every point on some interval from a to b. And if big F is any antiderivative of that function, now keep in mind that when we say any antiderivative, all antiderivatives differ by a constant. And when you take the derivative of the antiderivative, that's just going to drop out and leave you the original f, and that's effectively fundamental theorem part 1. Okay, so when you have that, and big F is any antiderivative, then what you can do is you can find that antiderivative and take big F of b minus big F of a, and that's how you can use the fundamental theorem to evaluate a definite integral. And we call this the evaluation part, because this is how you're going to evaluate definite integrals. Let's take a look at some more information here. This theorem says that any definite integral of any continuous function can be calculated without taking limits, without calculating Riemann sums, any of those RAM methods, and often without effort. So long as an antiderivative can be found. Now, you can imagine that this was probably a bit of a breakthrough at the time when this came together before computing machines. Approximations by tedious sums were the only alternative. You can only imagine that people thought that this was just, the best thing since sliced bread, at least mathematically speaking. Okay, so provided you can find an antiderivative of f, you now have a way to evaluate a definite integral without having to use the limit of a sum or any RAM method. Praise the heavens for that one. When applying the fundamental theorem of calculus, this notation is convenient. Sometimes what we would do, we would take the antiderivative, and I put it inside some braces, and then I put b and a on the outside of those braces, and then I do big F of b minus big F of a. And that's how I'm going to be showing my work for a lot of these problems that you will see not only here in this video, but also on answer keys. So for example, if you wanted to do the antiderivative, or the definite integral rather, of x third dx, you can write 1/4 x to the 4th, evaluated at 3 and 1, and then you can just kind of go from there. So it's going to be 1/4 3 to the 4th minus 1/4 1 to the 4th. And I think you could pick it up from there. It's going to be 81 over 4 minus 1 over 4, and this works out to be a final answer of 20. Let's take a look at a few examples here and see how we can zip through those and show you what to do. Okay, so x third plus 1 is the function, and we're going to evaluate this definite integral on an interval from -3 to -1 to +3 rather. Okay, so let's start with the All right, and now we can apply this to a couple of these other situations, and let's zip through these two real fast. So the antiderivative on this part A is going to be 1/3 x to the third minus 3x, evaluated at 2 and 1. All right, so going through the motions here, 2 cubed is 8, so I have 8/3 minus 6 when I plug in 2. And then I have 1/3 minus 3 when I plug in 1. So now, once again, I'm going to turn my attention to the things that have like denominators first. And I can see that that is going to simplify to 7/3. And then now I'm going to turn my attention to the constants, and don't forget that's a minus. So I'm subtracting a negative, which means I'm going to be adding. So it's going to be 7/3 minus 3. Okay, well, now I really want to get intentional about simplifying this. And it looks like I'm going to end up with negative 2/3 as the answer. Okay, so that takes care of that one. Now, how do you handle situations like what we have in part B? Well, we already know what to do. First of all, I'm going to pull that constant out because constants can pass across calculus symbols. Second thing I'm going to do is I'm going to be super selfish and rewrite that as x to the 1/2. So now I'm going to have a 3 on the outside, and then I'm going to have a 2/3 x to the 3/2. Now, how do I get that? Well, I have to add 1 to the power, making it 3/2, and then dividing by that 3/2 is the same as multiplying by 2/3. And I can evaluate that at 1 and 4. All right, now I'm going to handle the constants first because that's actually going to be easier. I notice that we can zap those constants right away, and I can just get that 2 out of the picture because it's just like distributive property at this point. So it's 2x to the 3/2 evaluated at 1 and 4. All right, well, let's go ahead and do this really quick and see what we end up with. 4 raised to the 3/2 power is going to wind up being 8. And 1 raised to the 3/2 power, gosh, I hope that's 1. So figuring that out quickly, 8 minus 1 being 7, that's going to evaluate to 14. All right, last example coming up. Oh boy, we have an example involving trig. And a lot of people will probably go, oh boy, this isn't going to be a whole lot of fun. Well, if you stop and think about what the antiderivative of this is, you probably know it, because the antiderivative of secant squared is tangent of x. And then we're going to evaluate that at 0 and pi over 4. And we all remember that the tangent of x is a bit of a pain to evaluate unless you are dealing with some easy functions. Well, we've got tangent of pi over 4 minus tangent of 0. Now, lucky for us, that drops real fast. Okay, so that's a quick little tutorial on how to handle definite integrals. A couple of quick things that you might want to remember when it comes to natural log and e. The antiderivative of e to the x is, of course, just e to the x. And the antiderivative of 1 over x is going to be natural log of the absolute value of x. That's important. Now, why is that important? Because, as we all know, the natural log has some domain restrictions that go on it. And if we don't take the absolute value of that, then we're going to run the risk of having some problems putting things together here. All right, so that's the introduction. I wish you good luck and have a great day.